Hi, everyone, and welcome to the second seminar of the semester. Today we have Leah Shteynman talking to us about zircon, Reidite, and shock minerals. And before we start, I wanted to give you the usual housekeeping. We have our links to our social media. Of course, this meeting will be recorded and available on YouTube the following week. You can sign up for a mailing list at forest.asu.edu/contact to know first when those videos are available. We have two more seminars this semester from our own Kyusei Tsuno and future Force faculty member Sibo Chen, who will be starting in January. And I want to remind you that the fourth winter workshop will be held here at ASU January 7th through 9th in person. We have the hotel block already, so you can visit that link. The group discount will automatically be applied to book your hotel. And the registration site will be opening soon, so keep your eyes out on your emails for when that will be announced. We have 3 confirmed speakers so far: Tomo Katsura from BGI, Baosheng Li from Stony Brook, and Mike Walter from Carnegie EPL. This year, the workshop is going to cover both science and the organizational structure and the future operating model of FORCE as we prepare to move from the implementation stage to full operations just 1 year from now. So without further ado, I will introduce our seminar speaker. Leah Shteynman is a PhD candidate from ASU School of Earth and Space Exploration. And before joining ASU, she received her undergraduate degree from Lafayette College and was an intern at the American Museum of Natural History, where she began her study of shocked minerals. She's applied her microscopy skills to studies of Martian analogs, such as Icelandic sands, and has received honors and fellowships, including the NASA Finest. Today, she's going to talk to us about shocked zircon/Reidite and how their textures and crystallographic orientations affect their utility in studying impacts. So Leah, you can take it away.
Okay. Hi, everyone. I'm really happy to be here today. My name is Leah Shteynman. I'm a PhD candidate in geology in the School of Earth and Space Exploration here at ASU. I'm really excited to get to talk to you today about my dissertation work on shock microstructures in zircon. So my talk title includes zircon and Reidite, which are zirconium silicate polymorphs, zircon being the regular one we think about all the time, and Reidite is the high pressure version. I'll be talking about both of them, but I'll also be talking about some other zirconia and silica phases throughout the talk. So this is going to require diving to a couple different phase diagrams. So get ready for that. Okay, let's get into the motivation. The big picture topic that I study is impact cratering. And I think a lot of people don't really know too much about it. So I'm going to give some background. What is impact cratering? You've seen impact craters if you've looked at the moon, if you've seen or visited meteor crater. Impact craters are formed by impactors much smaller than the diameter of the crater. This happens because the impactor has enough kinetic energy to generate shock waves in the target material, which travel faster than the speed of sound in the target. Cratering is a fundamental surface altering process on rocky bodies. Okay, I just saw the message. Thanks, Kara. So here's a little GIF about how impact cratering works. When the projectile hits the target, which can be solid earth, it can be water, it can be anything, it generates shock waves and rarefaction waves, so release waves that they really do the work of carving out the crater. The highest pressures and temperatures occur closest to the point of impact. That's where vaporization occurs, and then a little further radially out, that's where melting occurs. In small impacts, like the one that formed meteor crater, parts of the projectile can be preserved. So if you've been up there, you can actually find pieces of the meteorite impactor in the desert surrounding the crater. In this cartoon, those pieces are part of the ejecta. So that's the stuff that's landing kind of on the outside that's being shot up and out. In larger impacts, the rarefaction wave in the projectile completely vaporizes it. So we don't have chunks of meteorite lying around like Vredefort or Sudbury. Further out radially from the point of impact, the shock wave attenuates. So the energy is no longer sufficient to cause vaporization or melting, but shock metamorphism occurs instead. Further out from that, there's fracturing, brecciation of the target rocks, and the end result is a crater with many different impact-related rock types, and many of them are complex. So we generally talk about impacts as having 3 stages. The first one is the contact and compression stage. So the projectile hits and generates a shock wave going out in all directions. This compresses the target rocks. It pushes material down and out, and it also creates some vapor and melt. After contact and compression is the excavation stage. This is where the shock waves and the release waves really carve out the crater. So the excavation stage ends when that transient cavity reaches its maximum size, and that's when the modification stage begins. So this is stage 3. The ejecta lands, the crater has an uplifted rim, and the transient cavity is gone. The modification stage is considered to end when things stop falling. So that makes it kind of easy. The version of the crater that we see now depends on a lot of different things. So the projectile composition, its velocity coming in, its mass, the target composition, and post-cratering changes, which are significant on Earth. So regular geologic processes like erosion, deposition, and metamorphism, those can remove traces of craters to the point where we lose many of the products created by cratering or all the products. So we don't really have, rocks preserved from the earliest time on Earth. We don't have craters preserved. Notice how the vapor and the melt-rich materials here in that final crater cartoon, they end up near the surface of the crater because that's going to be important later. So what's special about impact cratering? Impact cratering and shock metamorphism can be difficult to study because of just how extreme they are compared to regular geologic processes. So here's the Earth's geotherm on a temperature pressure plot. Here's the pressure and temperature region that is occupied by normal metamorphism in Earth's crust. Here is about the pressure and temperature at the base of tectonic plates. And then this orange region on the right side represents the pressures and temperatures of shock metamorphism. Shock metamorphism encompasses many processes, but most simply, it just means changes that come from the interaction of a shock wave and material. It's pretty extreme if you just look at the pressures and temperatures. The time involved in cratering is extreme too. So the entire time from a projectile's impact through the end of the modification stage when things stop falling, that can be on the order of just seconds. As an example, meteor crater was formed in a few seconds. That's a pretty small impact crater on Earth. Larger, about 200-kilometer impact structures like Reidite or Sudbury formed in about 10 minutes. So still a pretty short time compared to a lot of geologic processes that we think about. The release of the energy in impacts is essentially instantaneous, the way we think about it. So this is the really dialed down version of this plot, but here's a more real version with real temperatures and pressures. So you can see shock metamorphism, it starts around 5 gigapascals and goes all the way up to over 100. And in terms of temperatures, I mean, they can be really crazy. So this really is special and different. At the lowest shock stages, you get these shatter cones. I'll talk about them a little bit later. You get diaplastic glasses, you get high pressure minerals, melting, vaporization. And you can see some of the phase transitions that occur during shock metamorphism. They don't occur where normal metamorphism occurs, but some of them do, like quartz-coesite. So the main motivation for my work has been the need for precise and accurate ages of impact craters on Earth. But why do we need to know their ages? Well, cratering has relationships with the geologic evolution of the Earth, the origins of life, biodiversification events, extinction events, and more. So how many crater ages do we have? Not many. So each line here represents one confirmed impact crater. There are about 200 on Earth with more waiting to be discovered. And the black lines are really the ones with relatively good ages. So let's dive a little deeper into that. Here's a plot of precisions of impact crater ages. About 2/3 of impact craters are considered undated, either because they have no age constraints at all, or they have an age with 10% error bars or more. Only about 1/5 of impact craters have precise ages within 2%. All of those precise ages have been acquired by 2 isotopic dating methods. So that's uranium-lead and argon-argon dating, which comes from potassium-argon dating. These methods both currently require impact melt or highly shocked materials. And that poses a challenge because those materials aren't present everywhere and they're not preserved everywhere. So this is another schematic of an impact crater. Like I mentioned before, the highest pressures and temperatures are closest to the point of impact. Even in large impacts, only a small amount of vapor and melt is formed. That melt region produces melt-grown crystals, which can yield very precise ages. But past the melt zone, there's also a region of shock metamorphism, like I talked about earlier. As you can see on the left side of this, even within that region, the shock wave attenuates significantly. So there's a big difference between shock features that are formed at 20 gigapascals versus 5. When we talk about shock metamorphism, that includes a huge number of different processes and structures that only happen at specific conditions, and only some of the products of shock metamorphism can be used for dating. Here's a simple plot higher shock level, higher pressure and temperature is up. So at the lowest pressures and temperatures, we get shatter cones. These are formed in whole rocks, and you can maybe kind of make out that they're all pointing in the same direction. These are not datable by current isotopic dating techniques that we have to get really precise uranium, lead, or argon ages. Closer to the point of impact in the shock metamorphism zone, you get planar sets of fractures, planar deformation features in quartz, and you can get microtwins in some minerals. The high shock levels are where we get materials that we know how to date right now. So high pressures and high temperatures cause phase transformations and resetting of isotopic systems, which is usually related to high temperature. But if we look back at the cross-section of our crater, the higher shock levels are only reached in a smaller part of that shock metamorphism zone. So realistically, only a small portion of the crater even contains materials that are datable by current techniques. So I'm going to redraw this and be a little bit more accurate. So we've got a smaller zone that we can use to date. Earlier, I mentioned how the melt and the vapor-rich products end up closer to the surface of the final crater. That's where the most highly shocked products end up too. Unfortunately, that's the part of the crater that gets eroded first. So it turns out that there are some pretty good reasons why so few craters have been precisely dated. So people are constantly asking this question, why don't we have more and more precise ages of impact craters? Well, there's a lot of variability. So smaller craters don't experience the high pressures and temperatures, the high shock levels that are needed to create high shock datable products. They also don't form much melt. And even if they do, geologic processes continue after craters are formed, right? So melt-bearing impact rocks are mostly closer to the surface of the craters, and they're usually full of glass, making them very susceptible to erosion and weathering, both physical and chemical. Even if datable materials are formed, though, the ages that they can record can easily be overprinted by post-impact metamorphism in the region. Geology continues even after an impact crater is formed. Then there's the issue of target rocks. So on the right here, this is basically the same pie chart that I showed you earlier. These are precisions of the impact crater ages that we have. I'm going to overlay the target rock types. So blue here is sedimentary target. If you look at this, you can see that sedimentary targets obviously pose a challenge for dating. This is partly because sedimentary targets often lack minerals that are suitable for dating. But I would say the biggest issue that we have right now is that we just don't fully understand the behavior of the uranium, lead, and potassium argon systems during and just after shock conditions. And that is where my work comes in. So I explore zircon as a dating tool. Zircon forms many shock microstructures, right? I investigate those shock microstructures as potentially datable materials. I don't necessarily do very much isotopic dating myself, but I think about it a lot as it is affected by the structure of minerals. So at the lowest shock levels, zircon forms planar fractures. With higher pressures above about 10 gigapascals, it transforms to a high pressure polymorph reidite. So this is also zirconium silicate, just a different structure. Reidite itself is found in many microstructural variants. I am not going to dive into those in this talk, but I have also done a lot of work on that. So if anyone's interested, we can talk about it later. With really high temperatures and pressures, we don't exactly know which level, but high temperatures and pressures, zircon also becomes granular. So each of those granules has a crystallographic orientation that differs systematically from the other granules. I'm going to talk about that a lot more later. At the highest temperatures, zircon and reidite are both no longer stable. So for reidite, this is above 1200, or actually, I think it's above 1673 for zircon at ambient pressure. That's centigrade. What happens is zircon and reidite, they're not stable. They decompose into mixtures of zirconia and silica, which may be crystalline as various polymorphs, or they can be liquid depending on the specific conditions. And I will show you that phase diagram later. There are a lot of other shock microstructures that are formed that I'm not going to mention because this is already a lot. This talk is going to focus mostly on granular zircon, but to talk about that, I'm also going to have to bring in reidite and decomposition quite a bit. So let's get into the dating. There are some good reasons why people use zircon for uranium lead dating. Under typical geologic circumstances, it does a pretty good job. So uranium directly substitutes for zirconium when zircon crystallizes out of a magma, but zircon strongly rejects lead. Over time, the uranium breaks down to lead, and barring unusual circumstances, the diffusion for both uranium and lead through zircon's crystalline structure, crystalline lattice, are exceedingly slow. The closure temperature of this system is quite high. It's about 900 degrees centigrade. This means that zircon can lock in an age when it passes below that temperature as it's cooling. There are some geologic processes that heat zircon up above that and disturb the isotopic clock, but there's not that many. So if we kind of know the history of the rock, we may be able to get a good date. And this is a really common technique that's used. Zircon is also really hard to physically and chemically weather. And since there are two different significant isotopes of uranium that are incorporated into zircon when it crystallizes, and they each break down into a different isotope of lead, we can measure all of those and we can get two different uranium lead ages. That is better than one. If we have two, we can see if they agree or not. So if they agree, that's called concordant, and much of the time we can say that it was a closed system, not always. When the two ages disagree, this is called discordant. And this can signal that there was an event or multiple events that disturbed the zircon and caused it to behave as an open system. Overall, that makes melt-grown zircon really good for dating since the high temperatures reset the uranium lead stopwatch. So impacts generate melt, right? Impact melt-grown zircons have been used to obtain some of those precise ages that I talked about earlier for impact structures. Systematically oriented granular zircon, microstructure that I mentioned a bit earlier, has also been used to obtain precise ages for impact structures. This microstructure isn't widely considered to crystallize from an impact melt, though. To give you a little bit more information about the microstructure, a normal zircon grain is a single crystal with a single crystallographic orientation. We can measure this with electron backscatter diffraction in a scanning electron microscope. Granular zircon is this shock microstructure where the zircon becomes polycrystalline and those different orientations have a 3D geometric relationship. So the one on the right is real data. That's one of my zircons. On the left, it's just a cartoon. This is granular zircon, and I'm going to dive more into those orientations right now. So here's a cartoon of a systematically oriented granular zircon. If we plot these orientations on a stereographic projection, we can see that the 001, which is the long C-axis of the zircon for each granule, they're all mutually orthogonal. They're all at 90 degrees to each other in 3 dimensions. This is also true for their 110 faces. Those are the skinny edges on here. Systematically oriented granular zircons are identified by electron backscatter diffraction, which maps the crystallographic orientations of each pixel. So it makes a map of the grain, but it also makes these pole figures. So if we see 3 clusters 90 degrees apart on both the 001 and the 110 pole figures, that is a smoking gun for we have systematically oriented granular zircons. If you know anything about this topic, you've probably heard them called friggin zircons before. And I'm going to talk about that later, and I'm going to explain why I am not calling them that. So like I said, some granular zircons have yielded precise impact ages, but not always. So systematically oriented granular zircons don't always yield impact ages. So we should probably correct our earlier statement. I said high temperatures can reset the uranium lead stopwatch, but it's not just high temperatures. It's also that those temperatures need to be prolonged. So prolonged high temperatures can reset the uranium lead stopwatch. Some granular zircons have fully reset uranium lead ages. Some are not reset at all, and they record the ages of the target rocks that they originally formed in. And some are partially reset, giving ages between the age of the target and the age of the impact. All of this from the same microstructure. So here's a plot from Jen Davis, her dissertation that came out this year. These are a bunch of grains. Each green line here is one grain of a systematically oriented granular zircon, and they're all from the ejecta of the Chicxulub impact structure. So you might have heard about that one. That's the one that's linked with the extinction of the dinosaurs about 65 million years ago. The ages of the rocks that were impacted here are shown by the gray bars. So this was a multiple target type impact. The age of the impact, which is independently known from argon-argon ages and uranium-lead ages, this is the dashed vertical line. So you can see that these zircons yield ages from the target rocks over here to the impact age and everything in between. It's kind of a bit strange for one shock microstructure. If the formation of the shock microstructure is dependent on high temperature that's prolonged, then you would expect maybe all of them to be reset and maybe more of them to be discordant because there could be later open system behavior. So it kind of makes you wonder, how does this type of granular zircon form? I'm first going to present the mechanism that is most widely accepted in the literature. That's called the Friggin mechanism. And then I'm also going to tell you about another idea that's been suggested, but I would say is not widely accepted, just as an alternative. So to begin with, we have to think about the high pressure polymorph of zircon, Reidite. On this extremely simplified phase diagram, Reidite is shown in pink and red. And here's a more full version of the same diagram. So this is from Timms et al. 2017. It's been built from a lot of theoretical and experimental data. So high pressure multi-anvil, diamond anvil, and shock experiments have constrained Reidite's formation to only high pressures. And there's really, once you get above this curve right here, there's almost no temperature dependence. And this curve is really a kinetic effect that somebody did a paper about that came out after 2017. So it's not incorporated into this phase diagram. Zircon and Reidite have been shown to have a consistent crystallographic orientation relationship in both experimental and natural samples. When zircon transforms to Reidite at high pressure, the 001 of zircon, so that's this long C-axis, is aligned with the 110, those skinny side faces of Reidite. And this can happen in 8 different ways because Reidite has lower symmetry than zircon. So they're both tetragonal, but zircon is the same up and down on the C-axis. Reidite is not because it's missing this other symmetry. So this relationship is the building block of the Friggin or former Reidite and granular neoblastic zircon mechanism that was proposed by Aaron Kavasi. So I'm going to tell you more about it. Here's the first part that we just talked about. We start with the 001 of zircon, and this is just going to show 2 of the orientations that the Reidite can form in, where those 110s are aligned with the 001. Reidite is metastable at atmospheric pressure. So at high pressure, you make the Reidite, you transform. But when you go back to regular pressure, if you have too high of a temperature, above about 1200 degrees centigrade, the Reidite is not metastable anymore. It's just unstable and it reverts back to zircon. So I haven't seen experimental evidence for this, but it has been theorized that the back transformation follows the same rules as the forward transformation. The idea is that the 110s of Reidite transform into the 001s of the zircon, just like what we had before, but this time in 3 variations, which are all mutually orthogonal. There is about a 5-degree spread in this relationship between natural zircon and natural Reidite, and the back transformation is expected to introduce about another 5 degrees of spread. So here's the model that Aaron Kavasi put out. You have a pre-impact zircon. This is the 001 pole figure. It has 1 orientation. At high pressure, it transforms to Reidite. You get 2 mutually orthogonal clusters to the original zircon. And then when that pressure releases and you have too high of a temperature above 1200, now you have 3 clusters of Friggin zircon. In his mechanism, he doesn't really talk about how it becomes granular, but through other papers, I think a lot of people talk about it as being like a recrystallization process. So it's not a melt involved process. This is the most widely accepted mechanism for how systematically oriented granular zircon forms. But I'm just going to call it granular zircon from now, and I'm not going to call it Friggin in case it's not always actually made by this mechanism. So here's another version of that widely accepted mechanism, but this is with my own data. There's an alternative model out there from Lisa Kovaleva. So in her paper in 2021, she proposed a melt model. So in her model, she says you don't have to make Reidite. What happens is instead of the really high pressures to make Reidite, you get extremely high temperatures to the point where zircon fully dissociates into 2 immiscible melts. One is a zirconia melt and one is a silica melt. Then it's very undercooled and you get zircon nuclei that are forming out of the melts. And then eventually those grow and they spin and they only connect with each other and adhere when they have minimized surface energy. And that relationship, the mutually orthogonal relationship, is expected to minimize surface energy. So by her mechanism, she says you can make this without ever making Reidite. So going back to these grains that I'm thinking about, why is there such variation in uranium lead resetting of granular zircons? I put together a plan. So I decided to look at multiple granular zircons at the nanoscale. The way that we identify them is at the microscale using EBSD, but nobody had really looked further than that. So now I'm going to talk about my work. The first step was to find granular zircons. So I picked a place on Earth that I thought I would find them. This is Rochechouart impact structure. It's in central France in what is called the empty diagonal. It's like wine country. It's pretty awesome there. And this is about a 200 million year old impact structure. I would say it's medium sized. It's relatively well preserved. We have impact breccias. We have some impact melt rocks that are very rich in melt. And then the target is mostly granitoid and gneiss. So what I did is I went there and I went to this Gross-Pius quarry and I said, okay, other people have found granular zircons there. Let me see if I can find some. Here's what the rock looks like. And I made thin sections of it. So I made thin sections of the Chassanon Swaibite. This is a polymicted melt-bearing impact breccia, and I'm going to break that down for you. So polymicted, it has clasts of many types. It has target clasts that are shocked, target clasts that are unshocked, target clasts that are granitoid, target clasts that are gneiss, and it also has individual mineral clasts. Then it also has melt clasts. So these are impact melts that were made and incorporated into the rock. And then the matrix has some melts in it, but it also has a lot of minerals. So what I did was I took each of the thin sections and I mapped it in an electron microprobe to figure out really what's in it, the chemical composition. So this is a backscatter electron map, which is average atomic number contrast. A lot of the time, people talk about it as atomic number contrast, but the average is important when we're talking about polymorphs that have a density difference. So they have the same chemistry, but Reidite is like 11% more dense. You can actually see that in backscatter electron imaging. So each yellow circle here was a zirconium hotspot that I mapped with WDS. So I went to each of these locations and I investigated. I imaged it at higher magnification with backscatter electron imaging. So here is the first grain that I'm going to talk about today. Here's what it looked like in context. All of this stuff around it is impact melt. You can see some clasts, you can see some shocked material, some unshocked material. And up close, here's what it looks like. So I look at this and I go, yeah, that's probably granular, but I'm not 100% sure. I found another grain that was also surrounded by a lot of impact melt, and I went, that's probably granular. This one's interesting because it's a lot more porous on the inside. It clearly had some kind of inclusion. And then it's also got this brighter contrast stuff on the outside. This is pretty normal to have a decomposed rim of zirconia and silica. This is most likely what this is. So here are the two grains side by side. And I noticed the differences. I noticed that this one has some bright material on the inside that's higher contrast. And I thought maybe that's Reidite. So I decided to map them in EBSD and confirm that they're actually systematically oriented granular zircons. So if you haven't done EBSD, it's a technique where you can do diffraction in a scanning electron microscope. You don't have to thin something enough that it's electron transparent. And as the crystal moves, you get specific Kikuchi line diffraction. And then we can just have software map it for you. So that's what I did with these two grains. So EBSD gives you a phase map. So this was basically all mapped as zircon. I think there were some little individual Reidite pixels in there that I didn't remove because I didn't want to lie about them being there. But when it's just one pixel, it's hard to tell if that's real or not. It also gives you an orientation map where the colors are different orientations for Reidite and zircon. And then it gives you band contrast, which is kind of how good the indexing of the patterns was. And then I also put the backscatter electron image that I showed earlier side by side just for comparison. So from this orientation map, we get pole figures for zircon. And you might be able to see that there are maybe what looks like 3 clusters on the 110. and the 001. So I would say this is strongly friggin' zircon, or strongly systematically oriented granular zircon. And then I did the same thing for the other grain. So here's that other grain. This one actually indexed as Reidite in a lot of the center here. These could be remnants. They could be granular Reidite. They could be remnants of lamellae. I'm not really sure, and I don't think we can really tell. But that's interesting because we did see that in the backscatter electron imaging. So you can already see that these two grains, while they have the same systematically oriented granular zircon microstructure, they're obviously not completely the same. So here's that band contrast, and you can see the orientations of the Reidite here, and then the backscatter. And then there are the pole figures. For this one, it's definitely harder to say for sure that there are 3 mutually orthogonal clusters. But in general, in the literature, this would be something that's clearly accepted as a systematically oriented granular zircon. What's nice is since this one has Reidite, we can actually see that relationship. You can see one cluster on the 001. You can see 2 clusters on the 110, all of which are mutually orthogonal and all of which actually overlap with the clusters for the zircon. So this is great. I got 2 systematically oriented granular zircons, and I'm calling one of them no Reidite and the other one Reidite granules. So the next step was preparing for TEM and STEM, which is the main technique that I used for this work. I did that using fib. So I sliced them. I'm not going to go too deep into the fib, but I sliced them so that they're thin enough for electrons to pass through. And then I did transmission electron microscopy and scanning transmission electron microscopy. So I'm going to introduce the types of images that I will be showing. This is a TEM bright field image with the objective aperture in. So this is like absorption or diffraction contrast. The vacuum here is bright, which is why this is called bright field imaging. Here's the scale of darker to brighter for diffraction contrast. Darker means it's diffracting more strongly. There are also contributions for higher average atomic number and thickness, but I would say it's mostly diffraction contrast. And then the objective aperture is in here. That's just to give it more contrast. So you can see it gets darker towards the left because it's thicker. So there definitely is contribution from all of those factors. It's just mostly from diffraction. So whenever I show one of these images, I'm going to keep this whole bar there on the left because I will be showing bright field images and dark field images, and that can get confusing. So here's a STEM dark field. This is a HADF image. Here, it's mostly average atomic number contrast. So brighter is higher average atomic number. There's also some contributions from thickness and diffraction. So these will be HADF images. So let's go through the first sample. This is the Reidite granule sample, these orange things in the middle here, indexed as Reidite and EBSD. So here there are no clear boundaries between the granules. The individual granules have varying diffraction contrast. There's kind of a linear fabric, and there are these tiny dots in what looks like fractures. I will go into those. So this is polycrystalline, and it has pretty high strain in some of the granules. This is our first piece of evidence. Then that planar fabric, you can see it a lot better here. It's kind of northwest, southeast. So we also have those fine-grained regions, and they're kind of between the granules. So planar fabric, that's our second piece of evidence we'll use. And then here's kind of a zoom in on some of those finer grained regions. And you can see some tight granule boundaries, which is interesting. So third piece of evidence, tight granule boundaries. And then really diving into those fine grained regions. These are about 15 nanometer crystallites. And we have crystalline zirconia and amorphous silica. So this is our fourth piece of evidence. So we've got polycrystalline, high strain, a planar fabric, tight grain boundaries perpendicular to that planar fabric, and interstitial crystalline zirconia and amorphous silica. All of this is pretty consistent with the friggin' origin, especially since we do have the Reidite granules in here. If you made Reidite and then you back transformed, most samples of Reidite that we have experimentally and naturally are lamellar. So they have a planar fabric, and you kind of expect that you would sometimes preserve that planar fabric if you back transformed from the Reidite, even if you turned into granules. The high strain would make sense if it's a completely solid state transition. Those tight grain boundaries also make sense. And then the interstitial crystalline zirconia and amorphous silica also makes sense because this is another phase diagram. If you start with a zirconium silicate and you go to higher temperatures, you start making combinations of crystalline zirconia plus a silica-rich liquid. Eventually you get to liquids, but that's all the way up here. These are really high temperatures. So something like this, something like this, something like this makes sense. To melt a cubic zirconia, you would need a very, very high temperature. So it kind of makes sense that we now would have an amorphous silica and a crystalline zirconia. It also makes sense that that would be interstitial to the granules because it should have been hotter there. So here's the friggin' mechanism. We start with a pre-impact zircon. We at high pressure make Reidite, and then high pressure dies down, high temperature takes over, Reidite back transforms to zircon. So this grain seems pretty consistent with friggin'. The other grain, the one that had no Reidite, this one is definitely more complicated. So here's what it looks like. We kind of have two distinct textures. There's an inclusion-rich area and an inclusion-poor area. And there's a planar fabric that's stronger in the inclusion-poor region. So I'm going to talk about the inclusion-rich region first. Here's what it looks like in that bright field TEM. So remember, this is mostly diffraction contrast. We have many inclusions inside of the granules, and there's high strain in some of the granules. But besides those inclusions, like not too much strain. Then if we kind of zoom in more, we see that there are some crystalline inclusions. You can see that by the interference fringes, and there are some amorphous inclusions. So we went to HADF and we said, okay, let's do STEM, let's do EDX, compositional mapping, and figure out what this stuff is. So we did oxygen, silicon, and zirconium, and we determined that most of this is zirconium silicate, likely zircon. I did do some diffraction pattern indexing, but I didn't include it in this talk. The darker stuff in HADF images is silica, and the brighter stuff is zirconia. I still need to identify what the silica or what the zirconia is, like what specific mineral. That's a work in progress right now. But we have crystalline zirconia and amorphous silica. So again, this can make sense. It's a high temperature thing. But what I need to do is identify exactly what kind of zirconia we have, because that will tell us where on this phase diagram we were, whether we had a monoclinic zirconia, an orthorhombic, a tetragonal, or a cubic, because there are phase relationships between those two. And both zircon and Reidite at high temperatures, at different high temperatures, become unstable, and they decompose to zirconia silica mixtures. So then we also have heterogeneous distribution of inclusions. For the most part, they're kind of all over the place, and there really are a lot of them. We also have layered granule boundaries. So right here, I'm going to kind of, actually, first I'll mention this. This is something I'm going to talk about later for the inclusion poor region. But those layered granule boundaries, they look like this. And this is something that has been noted before for granular zircon. This is just a close-up. Some of them are really kind of crummy looking, but mostly you can see that those inclusions, there really are inclusions. It's not like you have a huge amount of zirconia and silica exterior to the granules. So now I'm going to talk about the inclusion poor region. I have a bunch of HADF images. I can't confirm that some of this stuff right here is Reidite. That's a work in progress, but it's brighter than zircon and HADF imaging. So it has a higher average atomic number. I did EDX chemical mapping. It shows up as a zirconium silicate, just like zircon with no chemical differences. And it has the habit of microstructural Reidite lamellae. So it's likely Reidite, but I can't 100% confirm. That's something I'm working on right now. Then we also have these really tight granule boundaries. Really few inclusions in this type of inclusion poor region. And here's like a bigger overview. You see a lot of these granules where the interiors are inclusion free. You only see inclusions around the edges. There are grain boundaries that are perpendicular to a clear planar fabric. I'm just going to breeze through these because these are just some fun pictures. There's not really anything specific about them. This was just, I got lattice fringes in HADF, which was pretty cool. But I do want to talk about this. Here's one of those really tight granule boundaries. And here are some inclusions that are around the edge. So there are a lot of inclusions that are clustered at the borders of granules with inclusion. They're at the borders of granules that touch inclusion-rich regions, and they're arranged concentrically with zirconia towards the outside. So here's a bigger picture of that. So what created these textures? We have two distinct textures. Here's just all those pieces of evidence that we just gathered. And let's go through these models. So unfortunately, the friggin model doesn't explain some grains that have very high spread and orientation data. About 10 degrees of spread makes sense, but some of them have way more than that, including one of the ones I showed. It doesn't account for inclusions inside. We would expect there to be decomposition at the rims of a grain, maybe even the rims of granules, but not interior. But then for Lisa Kovaleva's model, how would you get a planar fabric in this situation? It's probably also not hot enough to melt zirconia. And there's not necessarily enough time for the synosis process where the grains grow large and rotate and adhere to minimize surface energy. So thinking through these phase diagrams, we said this one was likely friggin, but I have a different idea for the second grain. So I'm thinking a hybrid mechanism of formation. We start out with some pre-existing imperfections in zircon. This is super common. That creates at high pressure heterogeneous temperature. So Reidite lamellae form in some places, but in other places you do get some melting, and that can be partial melting. Decompression is faster than cooling. So with high undercooling, you get many zircon nuclei, and the Reidite back transforms to zircon, and you get granularization. The difference here is that I'm saying that these nuclei, they kind of remain closer to the edges. So they take a crystallographic blueprint from that back transformed Reidite, from the Reidite that's still there, and from zircon that's still there. As they're growing, this is a melt or a partial melt, so they trap inclusions of zirconia and silica. Eventually, the melt runs out. You get two distinct textures in the same grain, and you get this kind of structure. I think that these layered granule boundaries are from post-impact hydrothermal alteration, depositing new zircon in voids or eating away at old zircon. So it's possible that there is evidence for multiple mechanisms that form granular zircon. So what are the implications of this? Well, in 2020, Cornelia Rasmussen, she put out a paper. This was actually also about Rochechouart. So 206.92 million years old is the established argon-argon age for this crater. And she found that if you do depth profiling of systematically oriented granular zircon, that the age kind of changes throughout, and you can get multiple plateaus, some with an age that overlaps the impact age and some not with one of those. So sometimes you get really different ages. Sometimes you get really good ones. And then going back to what Jen Davis showed in her dissertation, you have some that give you the impact age, some granular zircons that give you target age, and some stuff in between. So if we start looking at more of these are the ones that I talked about today, but here are a couple of the other ones that I have done maps of. You can start to see that there are huge textural differences within this category. So this could be like a polyphyletic grouping, if you think about it in biology terms. So some of these grains, they have huge domains of a single orientation. Some of these grains have zirconia or silica embedded within granules of zircon. Some of them have remnant Reidite, some of them don't. Some of them have planar fabric, some of them don't, right? It gets pretty crazy. Some of them have, granules coming through, but then it seems like normal zircon on the outside. This one, you can see a planar fabric. Maybe that used to be Reidite, maybe it didn't, right? So kind of gets to be a lot. And it makes you wonder, there's a lot of diversity in this one microstructure. So could we potentially link degrees of uranium lead resetting with more specific textural variations within the category of systematically oriented granular zircon? Because maybe there are multiple mechanisms that can create this. So that is the last chapter of my dissertation, and it's something I'm working on right now. I don't have an answer to this question, but I hope that I will before I graduate. So that's my next step, to see if specific textures are linked to degrees of resetting in natural samples. And then talking about high pressure, I would like to recreate systematically oriented granular zircon in the lab. I think it's totally doable. And if anyone's interested, I would be totally happy to have a conversation about that. But yeah, nobody's done it, and it seems very doable. So thank you, and I'll take any questions.
All right, thank you so much, Leah. That was a great talk and like very clear and understandable too. Although I might be biased because I saw you give a poster about this before. So, asking our attendees if you have any questions, you can type it in the Q&A and I'll read it out for you, or you can go ahead and raise your hand and I will unmute you.
And please don't ask me to go back to any specific slide because there are 100 of them.
I had a kind of a follow-up question on something you mentioned early on. You mentioned that for the Reidite variants that you had some more ideas about those.
Yes. So I would say that's probably, I would call it the first chapter of my dissertation. I'm looking at the different Reidite variants in TEM and STEM. And what I found is that, so let me give a little bit of background. When Reidite was first discovered, it was just as these perfectly planar lamellae that were maybe nanometers thick in some cases. And then there were granules, and they were interpreted as forming by different mechanisms. But then more recently in 2021, they found a couple others that are larger, weirder, massive. Sometimes you can find Reidite that is an entire grain, could be like 90% of a grain. And they could form by different mechanisms. But what I found is that a lot of them look the same at the nanoscale. So the massive Reidite and the bladed Reidite, they really look like just super duper twinned lamellar Reidite.
Mm.
But I'm still looking into some of them. And the granular Reidite is hard to look at the nanoscale because it's very small as it's been defined.
Mhm. How small?
I think usually we're talking like less than a micron is the size in a sample,
Oh.
and there's very little of it in a sample. I actually haven't found any in my samples yet, but it should be in there because other people have found it in the same rock.
We have a couple of comments in the Q&A. Great talk, thanks, and great data and great talk.
Thank you.
And then, do you have any other questions from the audience? Okay, Katie Goss says, really great talk. Just to clarify, if you see granular zircon and Reidite in a grain, does this indicate that the ages you may obtain are disturbed, or would you expect their age to show the impact age?
Right. So this is a very big picture, and I think it's a great question. I think that if you see Reidite in a grain, chances are it's probably not going to give you an impact age. It may give you a target age, and it may give you something in the middle. Because when you make Reidite and zircon and you preserve it, there's usually a lot of strain. There's usually also fractures, like planar fractures, or there can be like concentric fractures or radial fractures from shock. So it kind of turns the zircon into an open system. I've done some dating of grains that have natural grains that have both Reidite and zircon in them, and they have insanely high common lead concentrations. So some of my grains had 80% common lead. That is not normal for zircon because, like I said before, usually when it forms, it doesn't take in any lead. So you would expect it to mostly be radiometric. You can't get a real age with 80% common lead in a zircon. And then the other question was about granular zircon. I would say if you see systematically oriented granular zircon, because you can have granular zircon without that crystallographic relationship. If you see the systematically oriented granular zircon, you may get an age of impact. You may get an age of the target. You may get an age somewhere in between. And I think that it could have to do with a lot of different things. It could have to do with multiple mechanisms operating, could also have to do with what happens after impact. So you have interaction with like maybe long-lived hydrothermal systems, maybe there's metamorphism, and you can end up with some granular zircons have a lot more porosity than others. They might have void space where things can pass through, things can be leached or deposited. So some people consider that maybe when you get bad ages, discordant ages from granular zircons, that it's because you have interstitial common lead or common lead phases. So that's possible. I would say at this stage, when you get a systematically oriented granular zircon, you cannot yet rely on it to give you an impact age or to give you a concordant age. We haven't figured out exactly which ones are going to give us good ages. So right now, it's kind of like um, they're a secondary thing. We want to get a good age on a crater already and then use those to back it up. So actually in
Thank
Jen
you.
Davis's thesis, she did this like single age plateau thing to show that you could use the granular zircons to get a good age for Chicxulub, but not a first good age, just a good age. Yeah.
Okay, any other questions? Okay, if not, then we'll thank our speaker again. Thank you, Leah, for a great talk.
Thanks
And
for
thank
inviting me.
everybody for attending.